Okay. Today and tomorrow. Okay. Okay. So don't leave the building at the end of the talk. Okay. So uh, I think that we can continue with the program. The next speaker is Rafael Ruggiero, that is going to speak about the Birkhoff problem for Lagrangian minimizing okay. Mi minimizing submanifolds. Okay, thank you, Rafael.
Okay. Can you hear me? Okay. On the stage. Because from here I have a better sight of the slides. I mean, if I'll try. Otherwise, I go to the stage. Okay. So, well, thank you very much for to the organizing committee that includes myself to speak in this to speak in this meeting. I'm very happy and honored to talk in this celebration of uh, Paul's 85th birthday. A long life and very important work. And I would like to tell a story. All of us have a story to tell about involving Paul. And I'm going. I have a little story that perhaps Paul doesn't remember. And I wasn't a student of Paul. I came from Venezuela to Brazil to study, dynamical systems at IMPA. And eventually, in '89, I started at PUC. And this was a very complicated time for the country. It was a lot of inflation, 5, 6 years after the end of the military government, there was a huge financial crisis. And the first, politics always, the first elected, democratically elected president of Brazil was a very corrupted guy, and the economical crisis, got deeper and deeper in the beginning of the 90s. And then that's when Paul comes into the story. The political, the university was passing through a terrible period. The academic ambience was, awful. And then Paul suddenly came to me one day and said, I think it's a good time for you to make a sabbatical year. A sabbatical year. So this, I took it. I took it as it's better for you to run away for the moment, and then if you want, you come back and see what happens. But so and then you put me in contact with the TNGs in the École Normale de Lyon, and then I spent a year from '93 to '94 in Lyon when I met Thierry, Damien coming from Toulouse, and who else? Sikoral. Oh my God, so many people important in my academic life. Joshi Mitsumatsu spent the same year in Lyon. So it was, one of the most, wonderful years from the point of view of research in my lab. It was crucial and determinant for my research career indeed. So when I came back in '94, Brazil looked like, Switzerland. Something happened that the crisis, vanished. The wages were fantastic in dollars. We went to, it's like, it's like Paul was a sort of foreteller. I don't know. I'm extremely grateful to you for this. This changed my life. This suggestion changed my life. So thank you very much, Nate. Let's speak a little bit about mathematics. So I'm going to talk about this, the Birkhoff problem for Lagrangian minimizing submanifolds. And the talk won't, I mean, I hope it won't be technical. It's a sort of a survey of some papers I have with some authors. And so let's start. So the motivation for the problem is this famous theorem by Birkhoff. So Birkhoff proved, I think let's say perhaps in the 20s, that if you consider an exact twist map, an exact error-preserving twist map of the annulus. So this means that the diffeomorphism that preserve the annulus, I mean the annulus is just S1 cross 0, 1. Then consider an exact error form in the annulus, and then F is a diffeomorphism preserving the boundary of the annulus, and inside the annulus is an exact, it preserves the area. And suppose that there exists an F invariant continuous curve homotopic to S1. Okay, then the conclusion is that the projection, the vertical projection, I will use this notation that comes from the fiber bundles. Then the vertical projection restricted to the curve is a homeomorphism. So this is called a graph of the vertical projection. And the curve is elliptic, and the orbits in the curve are minimizers of certain action principle associated to the exact form sigma.
Rafael, could you remind us what a twist map is?
I'll tell you in a minute, okay? So exact preserving twist map. So a diffeomorphism from the annulus to itself preserving the boundary is a monotone twist map if we write in coordinates of horizontal vertical coordinates the diffeomorphism. Then we have this, so the derivative of the first coordinate with respect to the second one is always positive, and F preserves the area form sigma, okay? This is just the definition. And some properties, some basic properties already observed by Birkhoff is that there exists a sort of generalized Lagrangian associated to the space of sequences of S1, and this generalized Lagrangian is associated to this diffeomorphisms. I mean, for those who are familiar with, with conservative dynamics, this Lagrangian comes from the generating function of the diffeomorphism. And then a sequence minimizes the action of this Lagrangian if and only if it is a sequence of horizontal coordinates of an orbit of F. So for this sort of generalized Lagrangian, the sequences of the dynamics behave like globally minimizing geodesics. Okay, so this I'm going to comment a parallel between this problem and the problem of Hamiltonian and geodesic flows. So this is more or less a picture of a twist map. So you see you have an annulus here, and when you apply the diffeomorphisms to a vertical line, then when you see is a curve that is always intersected by the vertical lines in just one point. So every image of a vertical line is a graph of the vertical projection. This is the twist property, and then an invariant curve that is homotopic to the basis of this, let's say, fibration. I mean, the annulus seen as a fibration should be also a graph. So every vertical curve, every vertical, let's say, every fiber of the annulus intersects the curve in just one point. Okay, this is Birkhoff's theorem. So now I'm going to, to make a crash course in Lagrangian and Hamiltonian dynamics to try to establish a parallel between the Birkhoff problems for twist maps and Birkhoff problems for Lagrangian invariant submanifolds. Okay, so I mean, the setting is a complete, C-infinity complete Riemann manifold, tangent bounded is Tm, and then we consider a CK tonally Lagrangian that is a function from the tangent bundle to A, I mean, the scalar function from the defined in the tangent bundle. That is a CK function with K at least 2, with the following conditions. The first one is that the Asian of L with respect to the vertical variables is positive definite at every point. And L is, the second condition is that L is superlinear in the vertical fibers. So meaning that if you take a Riemann metric, or any Riemann, there is an initial Riemann metric here. Then the limit of the quotient, I mean, in few words, the Lagrangian grows more than the norm of vectors in each tangent space. Okay, this is the Tonelli condition. Of course, if the manifold is compact, if this holds for let's say a Riemannian structure in M, then it holds for every Riemannian structure. So this is independent of the Riemannian structure. Okay, the Euler-Lagrange flow equation is this one. I mean, this I'm not going to repeat. This is a very well-known equation. It comes from applying the variational principle to the integral of the Lagrangian that is called also the Lagrangian action, of course. And then the Euler-Lagrange flow is defined by this equation. It's this gamma phi t of PV is PV is a point in coordinates in the tangent space. So P is a point in the manifold. V is a tangent vector, and then gamma PVT is the solution of the Euler-Lagrange equation, whose initial conditions are at t equal to 0 is P, and the tangent vector at 0 is equal to V. Okay, so examples, well-known examples: geodesic flows or Riemann metrics. Lagrangian is 1/2 of the metric of the norm of the square of the norm of the vector. This 1/2 is just a convention. The Euler-Lagrange equation, the Euler-Lagrange solutions are the geodesics of the Riemann metric. Mechanical Lagrangians, it's very close to to a Riemann Lagrangian, but you add here a scalar function to the norm, to the square of the norm. To the square of the norm, and then I'll show you later some pictures. Then this is more or less a setting. This was more or less a setting in the tangent space. The Lagrangian setting in the tangent space. Then I would like to comment a little bit the setting in the cotangent space, where Hamiltonians live. So the associated to the Euler-Lagrange flow, there is always a first integral. There is the energy. The energy is defined like this. The Legendre transform. It's a map from the canonical way to go from the tangent space to the cotangent space, canonical in many ways. It is defined like it is the image of PV is P, and the gradient. This means the gradient, the differential of L with respect to the vertical variables at P. Okay, and by the convexity of the Lagrangian, the condition in the Asian, this is a diffeomorphism. Okay, and then the Hamiltonian, there is a function, a scalar function defined in the cotangent bundle. And the Hamiltonian associated to L is just L composed with the inverse of the Legendre transform. Okay, and then the Hamiltonian. This has the advantage of introducing a change of coordinates in the cotangent bundle, such that the Euler-Lagrange equation with this, let's say, with this change of coordinates, with this diffeomorphism, the Euler-Lagrange flow conjugated by the Legendre transform is transformed in this system of equations that is, the famous Hamilton system of equations. Okay, so in the coordinates, of course, the change of coordinates is, this Q here is the coordinate given by the change of coordinates induced by the Legendre transform. Okay, then the reason why I pass from the tangent space to the cotangent space is because I would like to talk a little bit about the symplectic structure of the cotangent bundle. The Hamiltonian endos the cotangent bundle with a form that a two form that is minus, the omega minus the alpha that is symplectic, meaning alternate closed and non-degenerate, and the differential, the form alpha is this one. So it's very close to the length form in R2n. Okay. But here, of course, we are talking about the coordinates in the cotangent space induced by the Legendre transform. And if you wish, I mean, depending on your taste and the problem you're dealing with, you can either, I mean, work in the Hamiltonian setting or in the Lagrangian setting, because you have always the Legendre transform that it allows you to, let's say, pull back this form, and then you can work in the tangent space with with symplectic structure, etc., etc. Okay. From the point of view of the theory of twist maps, the Lagrangian in this case may be considered as a sort of generating function for the Hamiltonian flow or for the Lagrangian flow. Okay, and I'm making this parallel because so I'm going to compare the orbits of the twist map with geodesics, and they have really very similar properties. Then a Lagrangian submanifold is a submanifold of the cotangent space that has half the dimension of the cotangent space, meaning the dimension of M, of the manifold. And then the canonical symplectic form omega vanishes when restricted to each tangent space of the submanifold. This implies that the canonical one form alpha, of course, restricted to the S is closed, and then the energy of the, I mean, whenever the submanifold is invariant by the, I think I didn't wrote it, but the energy is constant provided that the submanifold is invariant by the Hamiltonian flow. Okay. And okay, so examples of Lagrangian submanifolds that are invariant by the Hamiltonian flows, that is the focus of the talk, appear in, let's say, Hamiltonians with symmetries. The basic flows of surfaces of revolution have lots of Lagrangian invariant submanifolds. Totally integrable Hamiltonians, I mean, this is Arnold-Liouville theorem. In KM theory, I mean, you perturb a totally integrable Hamiltonian in an appropriate topology, and then you will have lots of invariant Lagrangian submanifolds. But in general, you see, okay, so let me pass quickly to the sort of, I mean, dictionary from Birkhoff problems, I mean, from twist maps to Hamiltonians to motivate a little bit what is called a Birkhoff problem in the Hamiltonian or in the Lagrangian setting. Okay, so for twist map, the twist map will be, the role of the twist map will be the Hamiltonian. Okay, the Hamiltonian flow. Okay, the role of the twist map will be played by the Hamiltonian flow. And there is something missing here, but the Hamiltonian flow of the cotangent bundle, and I will focus on the torus. Okay, the vertical projection will be the canonical projection. I mean, okay, unfortunately, it is missing here, but I mean the vertical projection is okay. Thank you. The vertical projection is just the map associated to each pair of points in the cotangent bundle, the first coordinate in the basis. Okay, an invariant curve will be, the role of an invariant curve will be played by a Lagrangian invariant submanifold, and the generating function will be the Lagrangian of the Lagrangian action associated to the Hamiltonian. Okay, and then we can state the Birkhoff problems for Lagrangian invariant submanifolds. So there are two kind of problems. One of them, the first of them is somehow more topological than the second one. That is more, is more of the nature of calculus of variation. So the first one is the following. So consider a compact manifold and an invariant Lagrangian submanifold for the Hamiltonian flow that is homologous to or homotopic. Depending on in the literature, there are these two assumptions are quite common to the zero section of the cotangent bundle. Then this submanifold is a graph of the canonical projection. Okay, this is it looks like a theorem, but it is not still, it's not a theorem yet. It's almost, but you know, I will explain a little bit some of the, I mean, it's beautiful theory developed from the 80s, and I will explain a little bit some of the main results. And of course, the zero section is the set of points in the cotangent bundle of this form, okay? This is the first, let's say, let us call this the first Birkhoff problem. The second Birkhoff problem is, okay, the same setting, M a compact manifold and S a Lagrangian invariant submanifold for the Hamiltonian flow that is minimizing. So the assumption here is belongs to the context of calculus of variations, okay? While the assumption here is topological, okay? So this is something, let me, the first one is, no, sorry, okay. The first one is more or less, I mean, the assumption is this. Suppose that this is, imagine that this is the cotangent bundle. Imagine that this is the Lagrangian submanifold. And the assumption is that the Lagrangian submanifold is homotopic or homologic to the zero section. The zero section is, you know, you can figure out, you can imagine that the zero section is this, the basis of the, let's say, the annulus. And then this second problem is linked to the second, I mean, to the comments I made about, you know, this generating function and the generalized Lagrangian associated to the twist map that, you know, makes the orbits, essentially the orbits of the twist map minimizers for that, you know, generalized Lagrangian. And then minimizing here means minimizing for the action functional associated to the Hamiltonian or to the Lagrangian associated to the Hamiltonian. And then the conclusion would be that the submanifold is a graph of the canonical projection. Okay? So some comments, some general comments. So imagine that this is the cotangent bundle. So this is our submanifold here that is supposed in the setting, I mean, in the assumption of being, let's say, homotopic or homologous to the zero section. Then, of course, the study of the, I mean, to see if, to look if for the graph property, let's say for a Lagrangian invariant submanifold, you have to look at the singularities of the vertical projection or the canonical projection, which are just the points where the tangent space of the Lagrangian submanifold has some non-trivial intersection with the vertical bundle, okay? At these points, you have probably singularities. And then I'm going to talk, I mean, a little bit about the, you know, the symplectic side of the theory, because the first Birkhoff problem that is more, let's say, topological is, I think, perhaps the most developed side of the theory. And I would say that in the 80s, in the early 80s, the works of Polterovich and Viterbo, looking at the Maslow index, I mean, this is a problem of I mean, what they show, I mean, I'm not going to define the Maslow index because I don't have time, but what it is a sort of index of, I mean, if you look at the, sorry, I mean, this is, when you look at the tangencies of the tangent space, I mean, of tangencies between the Lagrangian submanifold and the vertical fibers, you have sort of critical points of the problem. And then the Maslow index is sort of an index for these critical points. And then what they show, Porterovich and Viterbo, is that, I mean, with very powerful symplectic topology machinery, is that when the Lagrangian invariant submanifold is homologous to the zero section, then the Maslow index it vanishes, or the Maslow's cycle vanishes. Okay, and with this, you conclude that the canonical projection is always a local diffeomorphism. Okay, so you don't have tangencies, you don't have critical points for the graph problem restricted to the Lagrangian submanifold. And then it was known by Arnold that this implies a graph property. So it was enough to have local diffeomorphisms. I mean, it was enough to know that the canonical projection was locally diffeomorphism to deduce, to conclude that it was indeed a diffeomorphism. Okay, so it's more or less the main idea. Oh, well, this is, I mean, there is a missing hypothesis here that has to do with dynamics. That is this one, chain recurrent. I mean, what they proved, I mean, Polterovich and Viterbo, is that suppose that the Lagrangian invariant submanifold is homologous to the zero section and that the Hamiltonian flow restricted to the submanifold is chain recurrent. Okay, then the submanifold is a graph of the canonical projection. Okay, so they somehow they needed not only that the Maslow's cycle vanished, but they needed this hypothesis that comes from the dynamics. Okay, and this is the 80s and early 90s, and then more recent developments by Fukaya Abu Zaid using flow homology to study what is called selectors of Lagrangian submanifolds. Show no, I mean they got results, very interesting results, proving the graph property for a category of Lagrangian submanifolds without involving dynamical hypothesis. Okay, so this is really a breakthrough in the theory, and one of the results I'm going to tell you in minutes has to do with an application of this theory. So now let me tell you a little bit about the variational side of the theory. So I'll focus on the case of the torus, and then let us lift the Lagrangian or the Hamiltonian to the universal covering of the torus. Let L tilde be the lift of, let's say, the Lagrangian, and then a solution of the Lagrangian equation of the Lagrangian of the L tilde plus K is called a global minimizer if the Lagrangian action, that is the integral of the Lagrangian L tilde plus K, is minimal in the curve, in the sense that okay, so in the sense that if you evaluate the action in any other curve joining the same points in C, let's say C T from CS. I'm going to look to show you a picture in a moment. Then the action in C is always less than or equal than the action of any of the Lagrangian in any curve. Okay, joining the 2 points, and this happens for every pair of points in the curve. Okay, the infimum. I mean, I put a K here because. I mean, in the case of geodesic flows, the K is just equal to 0. So you don't need any K to find globally minimizing geodesics. Let's say, for instance, in the Euclidean metric, globally minimizing geodesics are straight lines, and you don't need the K here. You just take the minimum of the minimal action of curves joining 2 points in a straight line, then it's attained in the straight line. Okay. But then when you consider any Hamiltonian, you have to put a K here because there is a value K such that under this value there are no global minimizers, and this value is called the Magnès critical value by the specialist. And so we are interested in global minimizers above the Magnès critical value. Okay. And then, okay, so this is an example just to show, to illustrate a little bit this phenomenon, I mean, this critical value in the case of the pendulum. This is the phase space of the pendulum, okay? So in the pendulum, you have this, I mean, the critical value, Magnet's critical value will be the critical value containing the saddles of the pendulum. You see, this is the one-dimensional pendulum. So you put the pendulum in an equilibrium position, and then you get this, you get a center here that is a steady solution of the Lagrange equation. And then you move a little bit, you give a little bit of energy, and then the pendulum will be like this. And then this gives rise to these periodic solutions here close to this center. And then the more energy you give, the more oscillation you get. And then at some point you get energy to attain the vertical position that is an unstable equilibrium point from the pendulum. And then at this point you have these solutions here that are in the level. And you see that these solutions are critical, you see? This is the circle, this is the representation of the circle, okay? I have to, the phase space of the pendulum is an annulus, so you have to identify this point with this point. And then this is a circle. And then you see that above, below the critical level, you have lots of Lagrangian invariant submanifolds that are not graphs. Okay, this cannot be a graph because it doesn't project surjectively on the circle. Okay, these solutions here, they always have singularities of the canonical projection. And above the critical level, you have always periodic solutions that will, wind and around and forever if you don't have any other force, any other external force acting. And then all these solutions are periodic and minimizers for the Lagrangian action. And all these solutions here, below the critical level, if you calculate the action in this closed orbit here, for instance, is negative. So if you make if you went around this curve here, the action will go to minus infinity. So this is why we always look at minimizers above the critical level. Okay, otherwise you cannot guarantee that they exist. And and then the definition of a submanifold that is minimizing is that every orbit in the submanifold corresponds to a solution of the Euler-Lagrange flow that is a global minimizer. Okay, so you consider your submanifold and a solution is a minimizer. If you project this solution in the manifold, you get a solution of the Euler-Lagrange flow, and then you lift it to the universal covering, and you get a global minimizer according to the definition of a global minimizer of the Lagrangian action. Okay, like a sort of generalized geodesic in the universal covering. And then it is known that every Lagrangian graph, once you know that the Lagrangian submanifold is a graph, then it should be minimizing. Okay. The point is that the second Birkhoff problem is that if the converse of this statement true. Okay, so this is more or less a motivation. More motivations, and then let me start with the middle serve. This is not exhaustive. There is a huge literature about this subject. It's a very beautiful subject. Here, so this is a survey of results of the, let's say, variational context, okay? So in the early 80s, Bialy, Polterovich, and Bangert came out with, applications with obrimated theory to show that continuous minimizing torus invariant by the geodesic flow in the two torus are graphs of the canonical projection. Okay, so this is perhaps the first result I know concerning this theory, and it has to do with the development of obrimated theory that appeared in the late 70s and early late 70s, let's say. And this was a breakthrough in calculus of variations, and this was one of the first applications I know in the problem, in this second Birkhoff problem, just in the case of surfaces, okay? Then with Mario Jorge Diaz Carneiro from the Federal University of Minas Gerais, sorry, Okay, so they proved this. I mean, Bial and Polterovich proved that a continuous invariant minimizing torus is a graph, provided that it has no closed orbits. Okay, so imagine an NGO example. Okay, so if you have an NGO example as a Lagrangian minimizing submanifold in the cotangent bundle of a Tonelli Hamiltonian, I mean of the geodesic flow, then this should be a graph. Okay, and then with Mario Giorgi, we found a counterexample. If the torus, I mean, you have minimizing tori, invariant minimizing tori with closed orbits that are not graphs, but just continuous. Okay, but then I mean, I'm not mentioning here, but then we showed that if you suppose that the Lagrangian invariant torus in this two-dimensional context is C1, then you get the same graph theorem. Okay, so Lagrangian minimizing two torus that is C1, it should be a graph. The base, I mean, the ideas of the proof of Bialy, Polterovich, and Bangert are, let's say, shortcut type arguments that appeared already in Morse's work. I mean, Morse has beautiful works about, you know, globally minimizing geodesics of surfaces in the 20s, I think, and then Hedlund for hyperbolic surfaces, and Hedlund's I wouldn't say the extended, but showed, you know, similar results for minimizers of metrics in the two torus. Okay, I'll show you in a moment some of the results of Morse and Hedlund. And then again with Mario Giorgi, we show that the graph property holds for smooth minimizing tori in the critical level of Hamiltonians in the two torus. And this is, I mean, this was interesting because this result was for geodesic flows. And for geodesic flows, the critical level is the zero level, so you don't have dynamics here. But if you consider Tonelli Hamiltonian, you may have dynamics in the critical level. Okay, but you may have singularities and all of that. So you have to use different kind of arguments to deal with the critical level. Then, okay, so this is more or less what Hedlund shows. If you take any Riemann metric in the torus, and then suppose that you have a geodesic here for this metric, with the property that when you lift the geodesic in the universal covering, then the geodesic is global minimizer, meaning the same thing that I told you before. I mean, the action, I mean, the length of the curve between 2 points is the minimal length among all the curves joining the 2 points. Okay, then Hedlund shows that well, many things. First of all, that there is a constant independent, I mean, just dependent of the metric in the torus, such that the geodesic of the metric is the constant is d, is in a d tubular neighborhood of a straight line. This is really remarkable. I mean, it's like a minimizer in the two torus is like a deformed straight line, but it still, you know, keeps a lot of the geometry of a straight line. And then Morse proves as well that when you project this minimizer in the torus, it has no self-intersections. So it should be a lamination or a simple curve. And this is used by Bialy, Polterovich, and Bangert to show, you know, the graph property for Lagrangian minimizing submanifolds in the two torus. Okay. So questions about the same problem in higher dimensions. I mean, the theory in two dimensions it doesn't extend, you know, to higher dimensions. The topology in two dimensions helps a lot to solve the problems. And then the first one I would like to address is, so do minimizers have asymptotic homological directions? Okay, this is one of the main problems of matter theory. I mean, matter has a notion of rotation number of or homology for a matter measure that happens to be the Schwarzman cycle. So what matter shows, I mean, one of the main objects of matter theory is a matter measure. There is a measure supported in an ergodic measure supported in a global in the projection of a global minimizer. Okay, like an environment supported in a globally minimizing geodesic, let's say, just to give an example of the geodesic flow. And then it happens to be that the support of a matter measures has an asymptotic homology. And this asymptotic homology coincides with the Schwarzman cycle. Okay? But, if you consider any, Lagrangian, let's say, even a graph. Suppose you have a graph, an n-dimensional graph, Lagrangian invariant graph, and every orbit is a minimizer. We don't know, perhaps it is not true, I think it's certainly not true, that every minimizer has a homological direction, you see. This is just, the existence of homological directions or rotation numbers is just for matter measures in general, okay? So this is one of the motivations of the results I'm going to show you in minutes. The second question is that does the minimizing property of the Lagrangian submanifold say something about global topology of the manifold, let's say homologous to the zero section, for instance? This is a very good question that it's been always in the mind of people working on the problem. If you suppose that the Lagrangian submanifold is minimizing because it's sort of a strong property, it looks like strong, then it should say something about the topology of the manifold. But it happens to be a very difficult problem. If you could say something, then you could deduce the graph property from the symplectic, let's say, point of view of the theory. Okay? The third question is, asymptotic direction. If asymptotic directions for orbits exist in a minimizing submanifold, do they coincide? I know, well, I'll show you in a minute that this is not true. But you may have, in higher dimensions, you may have an infinite number of, you may have many homological directions for the orbits in the minimizing submanifold. And the fourth question is, what is the structure of the set of singular points canonical projection restricted to the minimizing submanifold? This is, what can you say, about, the structure of the set of singularities? There is Matter and many other people studied Arnold studied the problem of this belongs to the realm of Lagrangian singularity theory, and there is a well-developed theory assuming generic assumptions. But in our context, there is no generic assumption because we have just we have just let's say invariant Lagrangian submanifold. If you put some generic hypothesis in the singularities, it suggests that you can perturb the singularity, the Lagrangian submanifold, and get this generic condition in the tangencies of the submanifold with the vertical fibration. But then, if you move the submanifold, you lose it. So it is not clear whether you can apply generic assumptions to a to a Lagrangian invariant submanifold. You have just one. You move it a little bit to get your generic assumption with the tangency of whatever, and then you lose because if you perturb the submanifold, you lose the invariance. Okay. So this is a very interesting question. If there is something generic that you can apply in this context for the singularities. And then some recent results with Mario Jordi. The first one is about the structure of the singular set. So what we show is that the singular set of the Lagrangian, suppose that the Lagrangian invariant submanifold is C1. then the set of singularities is a continuous ramified cross-section for the Hamiltonian flow in the submanifold. So it is something like a generalized caustic, you see? So any dimension. This is published in Discrete and Continuous Dynamical Systems. I mean, this is sort of surprising. I mean, it's because with no generic condition on the singular set, you cannot apply generic theories. And you know, you have normal form. When you have generic tangencies, you can apply normal forms and etc. You can describe very well how is the set of singularities. But you don't have any generic assumption here. Still, you get that the set of singular points the set of points where this is manifold is tangent to the vertical bundle is a continuous ramified cross section. And this allowed us to show that if every point in the Lagrangian minimized submanifold is non-wandering for the Hamiltonian flow, restricted to the submanifold, then the Lagrangian submanifold is a graph. Okay? I mean, actually what we show is that the points in the singular set must be wandering if the Lagrangian submanifold is minimizing. Okay? Because each time an orbit intersects the singular set, it's what is behind this is the notion of conjugate points. When you have an orbit crossing many times the singular set, this orbit gets conjugate points eventually. And there is a theorem of Arnold saying that in n dimensions, if you have a piece of orbit with no conjugate points, then contained in a Lagrangian invariant submanifold, then the points, the number of points of intersection of the tangent space of the submanifold along the orbit with the vertical fiber is at most n minus 1. This is a very nice theorem by Arnold. So if you have a wandering, suppose you have recurrent, or a point in the singular set that is recurrent, so you have a geodesic that intersects infinitely many times. Sorry. Oh my God. So you cannot have a minimizer that intersects infinitely many times the singular set, okay? Because otherwise you can apply Arnold's theorem and you get conjugate. And Marie-Claude Arnaud and Matter, etc., and many other people got some graph properties without dynamical assumptions. Then another theorem with Namari-Zorzi is like this concerning the graph property with some homological directions. Suppose that a Lagrangian minimizing torus invariant by the geodesic flow, some remanent metric, contains a rectifiable curve with totally rational homology, then the Lagrangian torus is a graph. Okay, let me show you a picture. So what is the the homology is this. Asymptotic homology is this. To take a curve here, you sort of make closed loops with longer and longer intervals of the curve, closed, let's say, by minimizing geodesics in the manifold, and then you lift this closed loop and look at the homology, and then you take the mean of the vectors, and if this exists, then there is the asymptotic homology. Okay, and then the homology is totally rational if the coefficients in any basis in integer homology are rationally independent. For instance, if you take a straight line in the plane with irrational slope, it is totally rational independent. Okay. So we got the graph property with this assumption, and then on the structure of the homological direction, this is a work in progress with Alfonso Sorrentino in Roma, in University of Roma III, and what we show is that again, a Lagrangian invariant. We consider a Lagrangian invariant graph for the geodesic flow of our remanent metric in the torus. Then the canonical projection of the geodesic flow restricted to the Lagrangian graph is conjugate to a suspension. So essentially, Lagrangian graph are suspensions. Okay, and this is the place when a little bit of foliation theory appears, but I don't have I don't have time to. This uses in the main tool here is a theory of foliations defined by closed one forms, because if the Lagrangian submanifold is if the manifold is a Lagrangian and is invariant, then the canonical one form is closed, and if it is a graph, then you can push forward the form from the cotangent bundle to a form in the manifold, and you get a closed one form in the manifold. The projection of the flow, I mean the graph defines a flow that is sort of the reflow of the manifold of the form, and then you can apply the theory of the foliations defined by closed one forms to the graph. And then the asymptotic homology of curves of the orbits in the graph is contained in a positive cone in the stable norm of homology. So let me show. This is the last slide. So what this shows is that there is an element in integer homology and a cone in the stable norm of the homology, such that all asymptotic durations of minimizers, if they exist, are contained in this cone. Okay. So you may have many, but at least you restricted. I mean, your directions, your homological directions are restricted to a positive cone. You cannot have any direction, okay, as homology directions of the orbits in a Lagrangian invariant graph, okay. And this is the final one. So thank you very much for your attention, and sorry for and happy birthday, sir.
Some fast questions or comments? No? So let's thank the speaker again.